Hello all. I hope I'm visible and audible.
Good evening, ma'am.
Hello. So I guess today only few of us are there. Well, do you guys have any doubts? I will go through the usual way. I'll go over the slides and then the assignment, previous year assignment questions. Or do you have any specific questions?
Ma'am, doubt related to assignment.
Yeah, go ahead.
Ma'am, I have doubt in the first question, ma'am, actually.
Okay, let me see. So, which of the following reasons result in erroneous classification of baby P and ischemic beats using the only signal length? So, do you remember what baby P was?
Yes, ma'am, bundle branch.
Block, yeah. So then they are asking here that what could lead to the erroneous classification of that and those ischemic beats if we had to use signal length. Now, if you have seen the slides, can you recall where the signal length was used? It's like through which kind of signals we did that. I guess that was there in the previous week also. So there was something called as minimum phase correspondent signals, where we always had a minimum phase and we had to look over the entire unity circle. So now if you see into the options that it said that of the normal and abnormal beats is always same, but it causes a second option is causes a wider QRX and hence increase in value of this, or ST segment elevation or depression can cause increase in the signal length. So just have a look that what changes, like what happens when bundle branch blocks or this ischemic beats occur. So which particular segment or which particular complex are we occurring for? Now obviously for abnormal and abnormal beats the signal length won't be same, because for signal length we won't always look into the duration of the signal, but we always look how the signal has been spreaded over the entire duration. So apart from that, have a look that okay, if there's an abnormality or a bundle branch block, what happens to the complexes? You'll get your answer there. um, Anything else? I can share my screen if you want to have a look at the assignment questions. um, Here, I hope it's visible. Just to characterize the signal, RMS value of a ramp signal for a causal signal. So you can even have an option over the limits also. Envelope and the Hilbert transform. Count of noisy EMG signal. It's again into the slides. Form factor. This is okay. The step, which step is correct there. Then again, okay. What all measures were there and which measure is correct? It's like correct representation of its own definition. And then last is envelope extraction will be useful where? Okay. So it's pretty fine. If you have a look into the slides, you'll be able to solve it. Do you have any doubts in the slides, or I'll continue the usual way? If you don't have any questions, you can let me know accordingly. Sri Naresh, do you have any questions?
No,
Oh, okay. So you want me to go through the slides, or do you want to have a look at the previous year assignments?
can go through the slides.
Sorry, I didn't understand. What did you say?
You can go through the slides.
You what? Both? Oh, you can go through the slides. Oh, okay. Okay, then we'll go through the slides the usual way. So, introducing myself, I'm Jagriti. I'm a second year PhD scholar at IIT Gandhinagar. I'm working with Professor Kala Shekhar, and currently I'm developing some quantitative ultrasound techniques for tissue characterization. One of my work has been focused into differentiating glioblastoma from normal brain tissue, and now I'm working on it, developing further techniques. So, the biomedical signal processing also that we are learning over here, I'm also employing some of these techniques into my own research. You like in week 6 lecture is what it deals with the envelope statistics as well as its Hilbert transform and all of those. So the primary step of making a ultrasound B mode image, that's a brightness mode image, is something that's taken the fundamental of this envelope statistics and has been grown ahead and ahead. So we have more signal processing techniques into the same. So previously we also learned the autocorrelation, cross correlation, then how signal varies over time, the averaging of the signal. So all those things are something which are necessary in the pre-processing of your data, post-processing it, and then finally doing some statistics. So I hope if you all do some PG program, say masters in or something, or PG or like PhD or something, you'll come across a course called as statistics now. In that course, you'll have a look at different kinds of testers and how do you differentiate if your data is statistically different or not. So that's again a furthermore step in order to see how your studies correlate, or are you able to differentiate in between the samples or not. So that's a way. So we'll go through the slides then. Sorry for this brief introduction. Okay. So VIX, okay. Week 6 has mostly dealt with the waveform analysis. So we are at week 6, and you all know that there are a total of 12 weeks. So we are just midway through the course. There are more 6 weeks. So hang in there and just continue to be this active and learning, keep this curiosity in yourselves alive. So we'll start today. First, in the last session, we saw that how minimum phase corresponding signals and their own signal length varied. So we also saw that what was a cepstral signal and how it varied and came through. So now here we see that the autocorrelation of this particular signal, that is represented by phi of x of n, that is of the x of n signal, it has a component that it, in a way, it is twice of the even component of the signal are x of n itself. So I hope that you know that how we derive an even component of signal as well as an odd component of signal. So plus both of them additionally, and then it's like how do you see if a signal is even signal and if it's an odd signal. If reversing the time gives you an exact interpretation of the signal, it's an even. If not, and it gives you the inverted signal itself, it's an odd signal. So in a way, in the cepstral domain, if you have to find the minimum phase correspondent of the signal, that is x of n, we see that for negative it's 0. But okay, wait a second, someone's joining. Okay. So we see that for negative the values are 0, but when it's equal to 0, there is most of the energy is being concentrated there. Whenever it's positive greater than 0, the waveform varies as that of the autocorrelation factor, where this over here is the complex cepstrum. So now we'll again go into the morphological analysis, that how our homomorphic deconvolution was playing a role into. Now here initially, if you all remember, that we take the Fourier, take our original signal, that's a time domain signal, take the Fourier transform, do its log transform, inverse Fourier transform. Now we have the x of n itself. Now this x of n, when we can do any sort of linear filtering or processing that you have to do, and that you want, and you can, it's like apart from using a non-linear matrix or methods, you can just employ the usual methods that you have, and then this kind of output that you receive through this filter or say any basic processing. Now this over here is into the cepstral domain. Now you take the Fourier transform, expand the signal again, and then take inverse Fourier transform. So the output that you get over here is the minimum phase correspondent part of the signal in time domain. So this is the way in which you can from the cepstral domain you can convert and interpret the minimum phase corresponding part of the signal. Next question that comes into play is that how do you find the signal length? Now, here the signal length is different from the signal duration of the or the extent of the signal. You might also think that okay, if a signal is corresponding from 0 to 2 pi, the signal length is 2 pi, but it's just the period of the signal. It's not actually the signal length. It's how that the energy is distributed over the duration or the spread of the signal. So it again depends upon the magnitude and phase of the spectrum, that we all know very well that magnitude we can get very few information from the signal, but phase is something that exploits most of the properties, and hence is one of the reason that why we convert into frequency domain and do our analysis there. So if it's a one-sided signal, then the minimum phase correspondent, it implies the minimum phase over there. If it's a minimum signal length, then it corresponds towards the minimum phase. But if it's a here one-sided signals mean that either your signal is causal or it's anti-causal. Now if the signal is what we say is like non-causal, then we can't say it's like ranging from negative infinity to infinity. This case won't apply over there. Okay, so how do you compute the signal length over here? So here our energy, so this is x square of n. It summation of x square of n represents the instantaneous average energy of your signal, that's x of n at each and every time point, and then it's weighted by a factor called as w of n. Now this w of n is a non-decreasing, so what we essentially mean by non-decreasing is that the signal is increasing, but it can't mean that it's monotonically increasing or linearly increasing, but it can also mean that after a period of time the signal can be saturated. So again, if we say if it's non-decreasing and increasing function, it's obviously a positive weighing function, and then we assume that when it starts at 0, the value is 0 and not some offset value through which we get a an intercept on the R curve. Then x square of n, it represents the average energy of the signal, and here the signal length has been normalized with respect to it. So now you might have an instinct or intuitive information from the signal length is that we'll get a signal length that's normalized so that the values would vary between 0 to 1. If you again multiply this factor to your to the signal length, you will get an absolute value of how the signal length is. But it's always nice to normalize the signal, because then you can represent it in some relative measures, and then it's very well nice to relate it from one measure to another measure. However, absolute values won't be that comparable when it comes to the case of it's like a signal processing or basic linear processing. So here the signal length, it again is like just to keep this in mind that it gives us the measure of the spread. Now this function over here, the weighing function, it can be linearly varying so that we get a centroidal time instant of this x square of n. So in a way it can be monotonically increasing if the condition of wn equals to n applies over there. Okay, so here in a way this represents the instantaneous energy. So what is the application over there? So we are now very well and nicely it's like we know that what ECG wave is, and then how the electrical potentials are created, how the circulation is. So we all know that QRS is a complex which occurs when ventricles contract or they depolarize. So this is action potential created by the myocytes, that those are nothing but the muscle cells. So the QRS duration over here is around 80 millisecond. However, if you see the entire duration of this QRS T complex, that is QRS wave and the ST segment, so entire this particular duration, so that duration ranges from 350 to 400 milliseconds. But then if you also notice that when you see the QRS complex, it's usually like this, and there is some amount of time when it is isoelectric. So no such it's like there's no wide movement or no instantaneous movements over there. So then entire energy is being focused into this QRS duration or this complex, that's around 80 millisecond. So we have, if we have a preventricular contraction that we saw in last class, that there were bundle branch blocks. So during this bundle branch blocks, a particular segment become wider. So what happens actually is that one of the ventricle will receive the response at first and the other will receive later. So accordingly it has been represented into left and right. So what happens there is this QRS complexes become more wider, because then you have two different peaks. So we also saw that how to differentiate in between these two peaks and how to say that okay, if it's a right one or left one. So we had different kind of precordial electrodes for the same. Okay, so going into this preventricular contraction, then we saw that this QRS and T waves, when this kind of contraction occurs, these waves are not separate, so they lack the ST segment over there. So it's again very difficult to or challenging to differentiate the QRS complex as well as the ST segment. Then what we saw that this and the normal wave will have it's like a similar magnitude spectra. So here, if we say that the magnitude spectra is same, essentially the phase spectra won't be the same. So there might be a change in location in the sorry, it's not location of energy, but okay, there might be a variation in the energy or how the energy is being varied from point to point. So here the signal length, again, it depends upon the magnitude and phase spectra. Just or home message for signal length. So then what we saw is that Murthy and Rangaraj, they proposed to classify in between a normal as well as an ectopic beat. Now, ectopic beat was something that we missed it, or the analogy of a hiccup. So to overcome the difficulty to determine the onset of the wave, the minimum phase correspondent of the signal, that is what we do over there is that we segment all P wave, QRX complex, T wave of each cycle, and then we use it for independent the signal length calculation. So there also what we do is like we determine the onset of a wave. So how do we determine the onset of a wave? So we know that from where initial starting point is and where it would end. Now essentially you don't need to have an exact better clear estimate that where it's ending, because you can't actually go into that precise milliseconds or microseconds, but you can actually have an rough estimate of it, how it's varying. So for classification, what we do is like we make a 2D map, and then we plot this signal length of this minimum phase correspondent signal against the RR interval. Now, RR interval is a measure of this heart rate variability. So through there, you can have an estimate approach that, okay, if the variability is varying between certain to certain variations, we might have this kind of thing, and hence the signal length corresponding to it. We have a it's like cross back validation that okay, it is correct. So what we saw was okay. So now the signal length is normally irregular for an ectopic beat, and it's normal for a regular beat. So again, it's better classification. It's in a way better if we do segment it differentiately on the basis of the onset of the waves. So when the signal length of the original signal is itself used, so we know that what's the signal length of the original or a reference signal, and then we are comparing it with respect to the different cases or the analogies that we have. So then what they did is like using this particular classification in here of the different ways, they classified it using a linear classifier. So if you are just like simply aware of, I won't go into the DLML methodologies over here, but that we have something called as like we make scatter maps, like we make scatter plots. So what we do over there, if we have something on the x-axis, something some other, these two variables are independent of each other. So usually what we do is like we plot amplitude with respect to time. So one is a dependent variable, other is an independent variable of the dependent variable. So now here in scatter plots, what we do is like we plot two independent variables, and then we see that what's the relation in between these two variables, and that's a mostly an effective or a reliable way of differentiating in between two plots. So we are well able to see. So here the classification is easy and the features are effective. So firstly, they classified 132 of out of is like 155 normal patient and something like this. Second patient, they were able to nicely classify. So initially in this particular initially when they were not classifying it and just doing it on the same basis, like measuring the signal length, they saw that everything was very clustered and random. But when they tried classifying in this method and segmented on the basis of the onset of the wave, they saw that okay, they were able to make a region where are two regions of say abnormal one or a normal one, or a person who's suffering from this preventricular contraction and a normal person, both were different, and we were able to differentiate them using, so we can actually make a linear regression, or can also see what's the cluster score over here. So there are different kinds of tests. One such test is called a Selhout square or Cohen's-d kind of test. So these are all statistical tests through which you can see that how well you are able to cluster and how well you are able to differentiate the two groups together. So what now we saw that first component of the waveform analysis, that was signal length and its measurements, its durations. So you have any questions on signal length measurements?
No,
If you
no, ma'am.
What are the
sure. Who was speaking?
ma'am? What are the cross and what are the zeros in the previous slide?
Oh, okay. So here, one such case is like there are no such legends weren't given. So you might see, it's like consider that one is a normal case, other is the abnormal one. So can be a normal case and can be a preventricular contraction case. So I'll just cross check through the textbook and let you know in the next class.
Okay.
Okay. So next we'll be going to the ECG waveform analysis. So we have gone through the ECG waveform analysis previously. So here we'll see that how nicely and it's like different kind of techniques we can use so that we can get a gross multiple picture of a waveform. So here the motivation. Okay, wait, someone's joining. Okay. So here the motivation is that we usually we do the correlation assessments as well as the signal length that we saw. So through these two measurements, we were able to get a gross picture. But then if you have multiple waves, you get the same value. So essentially better measurements are needed for to do accurate interpretations. So we'll go through the step of analysis, what people have done and reported in literature till now. So first is to detect the ECG waves. Initially, we detect them using a QRS complex. That okay, if you do have a QRS complex in your ECG wave, then okay, your heart is actually beating and it's beating to an extent that we can measure and the physician can make some diagnosis. So possibly the P wave or T wave, but sometimes the P and T waves, we all saw that these waves had a very lesser amplitude. The voltage values for them was merely in some microvolts. So compared to the QRS complex, I'm just talking relatively over here. So sometimes it's very difficult to differentiate the P and T waves with respect to the QRS complex. So always people do rely on these waves. So what we can do over here is that the previous thing that we saw there, that to measure the onset and offset is like how it starts and where it stops. So do the delimitation of the wave boundaries, like including the P wave, QRS complex, the T wave. So instead of the entire period, find the boundary where it stops and then where it ends. So all of their positions. Next, measure the interwave intervals, such as which lies in between them. It's like from one PQRST to other PQRST. It's like there are interval, then the PQ, then QT, ST segment, QQ, PP intervals, all of those. Now through these intervals, you'll be able to see some elongation, contraction, and that is obviously very visible through this measurement. So that gives you a quite better understanding of how there's a variation from one heartbeat to another heartbeat, how the cardiac output is changing from one cycle to another cycle. Again, you can also characterize a morphology, that's the shape of the waveform. So now here we saw some relative measurements. Now from here you were able to by getting the onset and offset values of this waveforms or waves, by delimiting them, you got the interwave intervals, and you can also see the shape of the waves. But then more and more characteristics will make more information. But then if there's more information, it's even more difficult to handle. Now the case of reliability of the measurements come into place. Like how do you know that which particular parameter is giving a physical significance of the particular property of interest that you are trying to look into it? So always it's not like, okay, stats people will say that we found the mean, median, mode, and we have done everything and each and every analysis of the signal and waveform. That was possible. But then comes this physics people, they'll say that okay, you did that, but what physical interpretations are you getting through your own signal? So I'll give you one such example. Now I have some data from my own say ECG signal. Now in that ECG signal, I do find some mean, median, mode, and all those stats. But then what do you know from okay, you can differentiate mean, median, mode from a normal signal as well as from a abnormal one. But then what do you know is like you'll just go to a conference and say that okay, I saw that the mean and median was differing from for this particular signal with respect to this particular signal, and then I did this much sample size was there, and I saw from this and this patients. But then what's the physical significance behind it? What it's actually telling you about the signal? So you actually need to know the underlying properties, inherent information for the same. So then people came around and they went through other different kinds of techniques. So one such is proposed by Cox is that the duration, that's the duration as well as the width of the QRS complex. So here we can see the height of it, the width of the waveform, how it's varying from one segment to another segment. Offset is like it's variation from the baseline of the signal, whether it's a positive variation or a negative variation. So your center is defined as the midpoint in between the highest and lowest bounds in the amplitude of this QRS complex. So it's not actually the center, say as origin or center as the baseline of this line, but it's actually the center of this particular complex. Then what they do is like rectify the signal. So what will rectification do is like make your negative components positive, and then you have the Q would be this small, this R would be this, and then S will be this positive. So you rectify it and then find the area under the curve with respect to the straight line through the midpoint of the baseline. So initially we saw that something as onset offset. So this is the way how which you can actually is like manually place some points and then measure wave intervals over here. So next comes another methods that envelope abstraction and analysis. So these are the same images from the lecture slides. So there what we did is like we took an EMG signal. So I hope that you all are aware. It's like kindly just you have a slight idea of how we had a carrier signal and a modulated signal in communication systems. So what we essentially did is like carrier signal was the signal that we had to send to the another end, and then we split it them into some chunks of information, and then we what we did is like modulated the signal with some signal that will protect the signal inherently, will deserve its own properties. Then we send it over the network, and then when we receive it, we dechunk the signal, decrypt the signal, and then we receive it our own signal. So in the same way, what we do is like we take the envelope of the signal. Now here, taking an envelope of the signal doesn't mean essentially mean that okay, we are sending the signal somewhere and then reserving its own properties, but we do take an envelope of the signal so that we get an approximate idea that how the signal is being looking. So you can interpret the data, you can visualize the data. So in a way, taking raw data is and then interpreting it is much more hectic with respect to doing some analysis on the envelope of the signal. So this is how it's like in layman approaches an envelope is as. Then we had PCG signals where we essentially you have some sounds that are like clubbed up, and then 4 different kinds of sounds, some which are only audible in in children's and some in adults. So these kind of sounds which are due to the closing of valves, opening, closing, which prevents the backflow preventions and all of those. So you can actually see that how the envelope of the signal would be essentially. So just few examples for the same. So then how do we do so? So the basic definition for a signal is like at any instant of time whenever it's varying with respect to, so we took an average of that part where T naught is the duration of the moving average window over here. Then we take the energy, define the energy for the same. So energy at particular instance of time. Uh, okay. And then the weighted function that we had initially. Now here the window is placed such that the signal is causal, and the weighted window function is like given by m minus k plus 1. Now here it's the duration of the signal by some instant at that particular point plus 1. So then this was proposed by Lehner and Rangayan. They proposed this moving average filter to squared PCG signal to get a smooth energy distribution curve. So this is just that how different people came and then they approached to a particular problem. Taking essentially a square of a signal helps in a way that you are getting rid of all the negative energy that you had in your signal. Because essentially, in the end, what you want is to measure the spread of the signal over the entire duration. It's not as if you have to see and that's like what we do in halfway filtering, what we do in full wave filtering, rectifiers, all those the same way. So what's the basic block diagram for this? Like, just keep in mind that choice of filter is a trade-off over here. So we take the signal, rectify it, do some filtering, and then we see the energy distribution, right? The critical step over here is doing the filtering. It's like if you take a full wave filter, you take a half wave filter, you do some low pass filtering, you do some high pass, band pass filtering. So in a way here, and then again in those kind of filters, you have different kinds of orders, the first order, second order, third order, for a butterworth, for a better low pass filter and all those. So there, the choice of filter, how many stages do you want in your filter, what cutoff frequency are you taking, how you're varying, what kind of buffers are you using in between, it varies and again helps curate your database accordingly. So though that was all for envelope extraction. Next we'll go into this amplitude remodulation. So let me know if you have any doubts for this couple of slides. That's clear?
Yes, ma'am.
Okay. Okay, so next is amplitude remodulation. So essentially, when we represent a signal, say y of t over here, x of t is our original signal, given by the phase of the signal, say cos omega t. So here there's a method called as synchronous demodulation. So we need a carrier signal here that's used in the transmitter, that's available in the receiver, including the phase of the signal. Then when we dechunk the signal, that's the demodulated signal. Suppose it's represented by xd of t. So we take this particular signal, multiply it by the cos omega ct. So it tells us about the carrier signal itself. So then again split the signal. So y of t was xt cos omega t. So xt of cos square of omega t. Distribute it eventually, and you know the property of this double theta angle. So we essentially utilize it, and we have half of it, half angle formulas. So when we apply a low pass filter, we get rid of this particular high frequency phase component from here. So what we saw is that this demodulated signal, in the end what we received was a scale version of the original signal itself in the demodulated signal. So what we get is nothing but a scaled version. We have our own signal, but the signal is crypted in a way, it's tricked to some fashion. So what we get is a scale version, but not always the original signal. Then what we do is like amplitude modulation. So now we saw that, okay, the process was this high, but we did some filtering. We were able to get rid of this particular high frequency signal. We got just the DC signal, original signal itself. So we had a gap in the process. It made our job easy to separate the signal. So again, we need a accurate estimation of this carrier frequency, that was omega ct, as well as the phase of it. So then if some error comes, it will again cause an issue. So better you know the absolute values of this variables of parameters, so that you can derive this half of x of t, or even if this value is very small, you get to know the value of this, and you get a very estimate or accurate value of your variable. So then there's a process called as asynchronous demodulation. So you don't have a sync to your carrier or modulated wave. So you're operating without a carrier signal, just in case everything is positive. So then you have some drooping characteristics. So here, this graph is again from the slides. So it's like lecture slides. So if you have a single sinusoidal signal varying, you rectify it. So the blue waveform, if you see over here, everything's positive. And then when you do low pass filtering to it, something you get is like, okay, it will decrease. Then you have the signal, then it will decrease. Yeah. So this kind of characteristics is called as drooping characteristics. Then we do something called as complex demodulation. So till here, everything was in real domain. We had phase of the signal, the real interpretation. Now we are going into the complex demodulation. So consider that you have an arbitrary signal. It's not unimodal. So you have multiple peaks in your distribution. But then what you do is like you estimate the center frequency, the harmonics of it, how it's modulated, and then what all waves or multiple of this particular waves will give rise to which particular signal. So if it's a sinusoidal signal, you get an impulse in its Fourier transform, essentially. So what this PSD is like point spread density of that particular function, or it can also be represented as point spread function, or the power spectral density. So it is, the energy is always concentrated at a particular frequency. Then you obviously need to estimate the amplitude and phase for each frequency band of interest. Suppose that, oh, if it's for this particular band or this particular band, or say in this particular band. So through there you can get an idea of that how the energy is being varied and how it is at the particular frequency. So if your signal of interest is something like this, A naught and cos of this given by the central frequency of phi of t with some initial phase to your signal plus the real part of the signal, then you decompose this cos part into the exponential of it is like e raised to plus jx and e raised to minus jx in your original signal. Now if you do after frequency shift by multiplication, now you multiplied it by the frequency shift, you got the twice of the component. Again you split it and decompose it, apply a low pass filter. The final result would be you get rid of this particular component, you just get the original signal itself over here. So then you find the magnitude and phase of the signal. So this is the magnitude over here. Magnitude of the signal essentially is this particular part, as well as the phase of the signal is this particular part. So this is how you did the amplitude demodulation. Complex demodulation is like just split the signal, find its magnitude response, the phase response. That's it. Apply a low pass filter, get rid of the complex part, and then have your original real signal. So where it is being used, it's all used for the analysis of heart rate variability and arterial blood pressure variability, also in some speech synthesis and analysis. So these are the kind of data set that people have worked on and have saw that, okay, using this kind of modulation, demodulation techniques helps us to differentiate and see how the pathologies and pathophysiologies are being changing. So next, one such kind of technique that's similar to envelope statistics, that is called as envelopogram. envelogram or envelopogram was something kind of that. So what we do over here is that we take the magnitude of this analytic signal that is formed here, the signal of interest, let's say that it's PCG. So PCG, that's x of t and its Hilbert transform. So we represent the signal that is y of t as the signal plus imaginary component of Hilbert transform. So I didn't say that what Hilbert transform here was, but what we do is like convolve the signal with 1 by pi t. So we get something for the Hilbert transform, something as this. Now this is very difficult to compute numerically, as well as there's no such kind of direct integral formula available for this or proof or theorem available for this. And again, for an analytic signal, the negative part doesn't give any energy over here. But just to give you an idea that what Hilbert transform essentially does is that here, so if you have a signal like this that's varying in time domain, if you take a Hilbert transform of your own signal, the envelope that you are seeing over here, this is the kind of process that Hilbert transform does, that it helps you take the envelope of the signal. So you can just go or scroll through MATLAB and you can see that there's a function called as Hilbert. If you apply it to any time varying data, you don't need to give the time as an input over there, but your RF data or say any time amplitude data, voltage data, you get an envelope of it. So if you plot them together, it's like the time domain data and the envelope of the data, you can see that okay, it's essentially the envelope of your own data. I guess I do have something to show. Okay, wait, I'll pull it up just to give you an idea. It's very similar what you saw, but okay, I'll just show. To the ones who feel bored, I guess this would be something different then. Oh, okay, wait. Here's only, do I have something else for the same? Okay, I do have. Okay, so here basically this is my research that I have done till now. So I'm not kind of overshowing something or show off or something. Just wanted to show you that. Okay, so this is a kind of ultrasound signal that you might have seen in sonography and so. So we have radio frequency signal over here, essentially your amplitude versus time data or voltage versus time data. When you take the envelope of the signal, now this envelope over here has been taken using Hilbert transform. So this is how it's dotted lines, if you see it, this how accurately and precisely at each and every peak of the wavelet it gives you the envelope of the waveform. So that was just an estimate. Just going to the slides back again. Okay. Okay. Next, so the Fourier transform of this 1 by pi t is negative sign of signum of omega. So what signum of omega is, like for negative part, it's negative 1, 0, 0. So it's kind of a step that's positive and negative. But then why did we take the Fourier transform of this signal? Because if you do the multiplications or the analysis in frequency domain, you can essentially multiply the signal with the signum of negative j of this omega. So that is like Fourier transform of x of n was x of omega times of this particular signal. Now this is always 1 plus signum of this. So what do you notice from this is like your output signal, that's y of omega, would always be a one-sided function of omega, because whenever you add them, it's like 1 minus 1 would be 0, 1 plus 0 would be 1, 1 plus 1 would be 2. It's everything very causal and going into the one side. So it's always one-sided function unless and until you take a modulus of it or anti-mod of it, it comes into the negative side of the domain. Okay, so what is the step of process that we do? It's like we first compute the DFT of the signal of interest, that's a discrete Fourier transform. You set the negative frequency terms to 0. Here I have given an analogy of how we do it in MATLAB. You just take the variable from 1 to n. Then what you do is like, now you had the variable from 1 to n. What you did is like, without realizing, you gave everything to the negative frequency as 0, but that's also your signal that you're looking into. You can't directly make it 0. So what we do is like, you multiply the positive frequency by 2, essentially duplicating the signal on itself. So the DC term over here will remain same, but what you get is like what you're expecting from there. And whenever you see a signal or take a Fourier transform, just go and do like, if the online version of MATLAB, if you don't have an offline version, so take a Fourier transform of any signal and then do F50 shift or do not do any padding or so, you'll see that the signal is symmetric across the 0 time domain. So if you take a double of it, it 2 won't do any harm, but it will essentially in the end will add up more information, and then you will give the exact interpretation of your data. Because we don't normally go into the negative frequencies, because people say that time is not negative, it always starts very causal and all. So in the same way, then what we do is like we compute the inverse DFT of the signal, and then the magnitude of the resultant signal, that's the envelope, it will give you the envelope of the signal. This is how we did the envelogram. And this is how I made that envelope that I showed you in my poster. Okay. Next are some measures that how we do the analysis of activity of a particular signal. Now here, this analysis is like there are 4 kind of analysis over here. First one of them is root mean. Okay. So do you have any questions in the first two? This envelogram as well as I guess this we did. Okay. Envelogram, do any one of you has any question? This part? If I was a bit faster, you can let. Okay. Okay. So next one is analysis of activity. So there are different kinds of activities that we do, and then essentially how I said initially that okay, we had mean median mode of a signal, and you do it and then present it somewhere, but you don't have a physical significance of it. So these are quite a few measures through which people make some physical significances, and through which they actually know that how the signal is being varying, and how you get quite like simplest bit interpretation of your own signal. So one such them of it is root mean square value. So it's being as like the square value of the signal and take the average of it, and then square root of it. So mean squared value, it's in its meaning, the definition lies over there. So this is a global measure, but there is a disadvantage that it makes use of the entire signal length. So it's not chunked up into some it's like it doesn't take into account that if your signal is like what we did initially, that we take the non-stationary signal we had, and then we make chunks of the signal, and then we made some quasi-stationary signals, and then we did our linear filtering or linear processing on those. So over here the signal length will vary because it's you taking the entire signal length into consideration. So average over the entire period is not that useful, because normally what we do is like during the pre-processing, what we saw that unless and until the mean is not significant, or you don't have any information about the mean of the signal, you blindly remove the average from your signal. So if you want the variation over time over here, what you do is like you find the running estimate of the root mean square. So this running estimate of root mean square that is like varied at instants of time. Apologies for this curly brackets, it was supposed to be square brackets over here. And then you do the same thing, but then you vary the signal and delay the signal accordingly. So if it's 0, then again 1. So it will vary and then give you the entire estimate over the duration of period of time that you're working into. So, but there's a inherent assumption for this, that the signal should always be a 0 mean signal. That's it. Next is the zero crossing rate. Now, zero crossing rate, a very nice term for it is, it tells you about the busyness of the signal. It's like the number of time the signal crosses the zero activity line or the line over the moving window. So it's again sensitive to the DC bias, the baseline drift, the low frequency artifacts, in a way that if your signal has some noise, a slightest of noise, then it will cross the zero line or the baseline line, and you might notice that particular crossing as the zero crossing rate. So that shouldn't be the case. So what we do is like people came up with another idea, and they saw that okay, let's take the derivation of the signal. So essentially if there are very smallest one, they will be cancelled out and would be 0, because we'll do some filtering in the end and then apply the z cross it's like zero crossing rate. So we take the zero derivative. Now here derivative is not but a simple high pass filter. So what it will do, it will remove the noise, make the DC bias as 0. So it will remove the R, whatever confounding factors that we had till now, it removes them. Next, such applications for this zero crossing rate is like for speech and silence decision, voiced and unvoiced sound discrimination, then PCG analysis for the detection of murmurs, say stenosis, or the calcification of word where some buildup is being there. So another such is turns count. Turns count, it tells us that the level of activity. It's very similar to this zero crossing rate, but it's different in a way that here we are looking at how the waveform is changing over the extreme masses, like how many times it's turning, but not how many times it's turning or crossing the midline or the baseline. So the change in turn and the boundary. Here also we take the the derivation, because through that you get an exact idea that how many turns it's been calling. But even if you don't do that and find all the maximum peaks, you will also get the turns count. So the it is what is like the physical definition for that is like number of spikes that are occurring in an interference pattern within a particular moving window. So this doesn't apply on the signal length or over the entire duration of the signal. So what we have as a change in phase, how we notice it is like through the direction or the slope of the signal, and that is called as a turn. Last factor of all of these is the form factor. Form factor, what it tells us that, so okay, I like to ask that how many of you know form factor as something that is it's like on the device point of view, or form factor what we saw in possibly it's like you might have a subject like that in digital electronics, or I guess it was in electronics. And then there's one other form factor in control signal processing. uh, I don't know many of those, but it's like one such I know, and I know the definition for that is like how it tells how compact your system is, what the form is like, how can you use your system, where can you translate your system, where. So that's also a particular definition for form factor. But the notion for this, it where it's like essentially the meaning of this is that how well you are able to differentiate a system from another system, how well you are able to make your system translatable. So here it's a notion of variance. So it tells you a measure of the EG activity. Now here, how do you measure activity is like by the variance of it. How do you measure variance is the square of the standard deviation. Then there's another term for it, that's mobility. So how do you measure mobility? By the square root of the ratio of activity of the first derivative of the signal to the activity of the original signal. Then what you do is like you find the complexity of the form factor, that's a ratio of the mobility of the first derivative of the signal to the mobility of the signal itself. So all of their formulas are same in their way. It's like first signal by the signal, original signal itself, form factor is like mobility by mobility. And so the it's like if you know the definitions for the same, you'll be able to derive the formulas from the same too. So any doubts? I hope I covered it, and I hope we'll be able to complete it faster today. If you have any questions or doubts, then we'll go through the slides. The assignment are 10 questions and we'll be done. I'll go through the slides again. If you have any doubts, let me know, and then we'll go to the assignment there. Any questions?
No, ma'am.
Okay. So we'll go through the previous year assignment questions then. Please do unmute yourselves and feel free to participate. So the first question, for analysis of signal using signal length, which of the following statement is true? If it depends on the energy distribution over the duration, if it's defined as the duration of signal, does not depend on the magnitude, does not depend on the phase spectra.
A.
Yes. So it depends on the energy distribution over the duration of the signal. Okay. The weight function in the signal length is the definition is it's a it's decreasing negative weighing function with 0 as 0, non-decreasing positive weighing, non-decreasing negative weighing, or increasing positive weighing with some other initial condition.
B, the non-decreasing.
Yeah, so which one, B or C?
B.
B. Oh, yes. So it's non-decreasing with a positive weighing function having an initial value of 0, so that we don't get an intercept or offset in our signal. Then compared to normal beats in ECG signal, the preventricular beats have which kind of QRST segment, or what happens to the QRST segment and the complex? Go on, go on.
Ma'am, wider width of QRS segment.
Yeah, so I guess you know the answer for the question that you asked previously then. So the answer is the wider width. Okay. Then Cox et al. Developed a
But
few
in
measures. Yeah, go on.
ma'am, but in that question, ma'am, it was given that the QRS segment is longer, not wider. Actually, this was my doubt. And
Sorry.
ma'am, in that question, in B option, it was given that bundle BBB, ma'am, it causes the longer QRS complex, but actually it's wider, not longer.
Options are longer like that.
Yes, ma'am.
I thought that I saw something else. See? Where it is longer. I am not sure that if B is an answer over here. I don't remember what happens to the ST segment, but longer is not given over there. I guess it's the same assignment, right? That we both are looking into. Okay, we'll go towards assignment R. If you have any questions, you can stay back and you can let me know. Okay, we'll first finish this part. So, okay, the answer for this was for the wider width of the QRST segment. Next is Cox et al. Developed a few measures to characterize the ECG QRS complexes. So, which of the following measure definition is correct? Okay, duration, height, offset, and the area under the curve. So just read through the slides. Read through the definitions and let me know that which particular definition you think is correct and would apply for the physical waveform over here.
Ma'am, in my question, ma'am, actually I missed the two words, ma'am. Actually, during the lecture, sir told that the result is longer and possibly jagged QRS complex. The result is longer QRX. Ma'am, and in question it's given wider. Actually, I changed the two.
Okay. No, it's fine. But he also said that if it's a longer one, the complex. So okay, let it be. So what do you mean if it's if the complex is longer?
Ma'am, maybe the amplitude is varied.
No. So if the complex is longer, doesn't essentially mean that the amplitude is increasing. It takes some time. It is spreading some over some time. So I hope you can. But I'm not so sure if B is an answer. I don't have an idea about the ST segment over there. So have a look into it also.
C.
This is Yash, I guess. Okay. We'll see. Offset is the vertical distance from the lowest point of this to the center of the QRS complex. So, why do you think it's to the center of the QRS complex? And it was the vertical distance from the highest as well as the lowest point, not only the lowest point. So here they said that the answer is B. C can also be the answer. B is like maximum amplitude minus the minimum. Okay, so most correct is B. Then area under the curve to the end.
Oh,
Okay.
sorry, it is
Others.
written lowest point. I have not seen that.
Okay, it's fine. Okay, so Lehner and Rangayan developed a system to obtain energy distribution curve of a PCG signal. The energy distribution curve is given as where x of n is a PCG signal, WK varies as this, and M is 32, with the signal sampled at 124 hertz. 1124 hertz. So we saw, I guess, the definition for the signal where energy was square of the signal with the weighted function. So which option can it be? Is it the B option or is it the D option? Or I guess others or because now you know that if it's energy, it has to be squared of the signal. So then, is it the B or D one?
Is it the D one?
Yeah. Yes. Then Which of the following statement is correct for the complex demodulation of the signal? So we saw that complex demodulation too, right? So here they say that it's demodulated to derive the amplitude and phase characteristic for the entire spectrum or for each frequency band of interest, or a Fourier transform of the signal is obtained. I guess it has to be an MSQ, I'm not so sure. Or the signal is obtained and the DC coefficient is made 0 for further analysis. Which option do you think can be the most appropriate over here? Which one, guys?
It is used to derive amplitude and phase characteristics, but I am confused in the entire frequency spectrum or each band of interest.
Okay. Do you want me to go to the slides back? But we saw that what complex demodulation was. Okay. Then we also saw that entire frequency spectrum wasn't used, but signal length, and there's something in signal length, we saw that something was for the entire duration. But then in complex demodulation, it was for it's like we had a signal, then we wanted to know it for that instant of frequency and then for the band of frequency of interest. So it's for each frequency band of interest. I hope it's correct. Okay. Next question. Sakadi et al. Proposed an algorithm for the envelogram estimate of the PCG signal. Following options show steps involved in the algorithm. Which of the following steps is incorrect? So we computed DFT. We set the negative frequency terms to 0, square the positive frequency terms, keeping the DC term unchanged, and compute the DFT of the signal and its magnitude is the envelogram estimate. Which option is incorrect here?
I'm option C.
Yeah, yes.
Option C, huh?
Yes. Okay, so I hope you all remember the formula of RMS of a signal. So that was like average of the square instant of the energy and square root to it. So where x of n is given by this, assume that here I don't think so 0 matters because it's just the x of n. Square them all, average it, take the square root, let me know what the answer is. Do you want me to
Is
pull
it
up
one?
the... Huh? Yeah.
Is it one? Option D?
I'm not sure. You did it. Let me also do. You took the average also?
Yes, just a
I do hope so. Yes. So the original signal, because that value by 8. Okay, 8 by 8.51. Okay. So why is it advisable to measure the zero crossing rate of the derivative of the signal? So what does the derivative do over here? So it will remove the high frequency noise of the signal, or will enhance the low frequency content, or will make your signal more smooth and help to get the correct value of ZCR, or to avoid an effect of the DC bias, the baseline to wander on the ZCR value. I do hope so. This should be an MSQ, but let me know what you think could be the most relatable one.
We have seen that in the derivative part, we have used the high pass filter. So it will remove the low frequency noise as it is the high pass filter. So it will make the signal smooth and does help to get the zero, the
Yeah.
correct. Yeah. See?
Yes. Yeah. C and D, both of these possibly, because these also is like we get to remove. It's like we have an high pass filter, so it will remove the low pass values as well as how the baseline is drifting or wandering from the ZCR value. So both of them are correct. Here D is the only option given, but okay, it's fine. Yes, this was it. Okay. Then if the frequency of the signal increases, its turn counts. What happens to the turn counts? So take it in a way that frequency of the signal is increasing. So the period of the signal is increasing. How does the period of the signal changes, or what happens to the number of cycles? So if the number of cycles increases or decreases, I'll
Increases
just
the
yeah, yes. So it increases. So causes the number of counts to increase. Thank you. If you have any question, let me know. If you want to stay back and ask me, that's also fine with me.
Thank you, ma'am.
Thank you.
Thank you.
Thank you.
ma'am.
Huh?
Can we come to the assignment?
Uh,
The
previous year ones or the one that we saw now?
latest one, latest
Oh, okay, this year's. Yeah, sure.
one. Can we get to the 10th question?
Okay, here.
Like, I'm getting confused in it. So, can you explain me that?
So for
Like how
the
it
following
is?
will be useful, where integrate high frequency variations are important, where general trend in the level of overall activity might convey useful information, where general trend in the level of overall activity does not convey, where for a signal, where so it's said that where the envelope abstraction is useful.
I'm confused in the B and C because we have seen that envelope abstraction, we do a
Hmm.
envelope of a signal. Like we take the
Hmm.
envelope of a signal, like in the
Hmm.
PMG signal example.
Hmm.
So that is a useful information also.
Yes, but I guess the shape of the waveform also tells you many things. High frequency variations won't be there. It does not even convey the general trend of the information, but because
Like
general,
where it is useful, envelope extraction where it is useful. So matlab,
we saw that okay, it tells us
that-
about the modulation of the signal, the morphology of the signal, the frequency content information of the signal. So also overall how the signal is being varied, how the information is there in the signal. So not only the individual time points of instance, but everything, all at the particular window point.
Hmm, okay.
I'm
Hmm.
also confused in between two options over here. I can't say that loud, or else NPTEL people will show me. But yes, I guess if you think it again thoroughly or see the envelogram wala slide, you'll be get to that. You'll have an idea.
Okay. And can you please switch to the first question?
Yeah, sure. Yes.
Is which of the following reasons results in erroneous classification? So I'm fully confused in it. Like these
So
are
they
two
has
correlated.
yeah check boxes, huh? Okay, MSQ. Okay.
Too many correlated subjects. So can you give me a glimpse to the triple B ones, which help me in
Sure.
that in these questions?
So last time we saw that how the bundle branches was varying. So if it was for the right one, there would it's like essentially there were two peaks in our waveform. So one of the ventricles will contract once, the other will contract a bit late than that. So we had the complex was more of wider in a way. It had it's
Wider.
like Yes.
We have discussed it in the last assignment hour
Yes.
only, last week
Yes.
assignment hour.
Yes.
I'm not confused
So,
in the B, so I get the okay.
okay. And
Okay,
then
okay.
here I was sure about B, but I'm not so sure about C, because now we saw in the slides that okay, signal length it obviously varies for normal and abnormal beats, so it's not essentially the same. But what happens to the ST segment if it's elevated or depressed? I don't have an idea, because the ST segment is normally more of an isoelectric segment. Bundle branch blocks don't have
Like
an.
in one of the bundle branch block type, like right or left, that I don't know, but
Hmm,
I think in the QRS part,
hmm,
between P and Q segment there is a spike in one of the
hmm,
type, and
hmm,
in one of the type Q and S or Q or T between there is a
hmm,
spike.
hmm.
So maybe it is the case of ST segment will elevate,
Can
but
or cannot. That's why I'm not so sure over there. I have to look
and
into it.
we know
But
that signal length is the estimate of the power
spread.
spectrum, so
Yes.
it can increase the SL signal length.
Can if it's differing or not, but if it's said on the basis of this two basic pathologies given over here, that's for the bundle branch block and ischemic beats, so you might have to look that if the segment is varying for this two or not, and
So,
that to be using only the signal length. So then again it's within a window, and then how the spread of the signal is there or the particular duration.
and we know the signal length is the estimate of the energy. So the option A, normal and abnormal beats are always same. Means so, is there any spectrum of normal and abnormal beats so that I can compare the things out related to
I
signal
don't
length or any
think
further
no,
statement?
I don't think
I
so,
don't
because
think that it is correct, the
huh,
option, but okay, I can't discuss this. Okay, okay.
we can discuss this next week though, but not now, I guess.
Okay, okay.
Okay.
Just to get an idea
Yeah.
so that it will be easy for me
Okay, okay.
because
I
the
think it's
options are
okay.
quite confusing.
Yeah, exactly. So I'm not usually involved in the making of these questions because they feel that I'm too young for this. So they are like, okay, I'll crack the questions in front of the students. So they don't usually involve me in that process. So I even don't know the actual answers to this. I get the answers one day before the class sessions. So that's why.
Okay, that's okay.
Okay. You have any other questions? It's fine.
No, ma'am. Thank you very much.
Okay. Thank you.
Thank you, ma'am.
Okay, so I guess today we did it pretty nicely and fastly. So we'll be closing for today's session then. Thank you.